Okay, on to Trig, chapter 12. So a lot of this stuff will seem familiar, at least, from geometry. I'm going to draw in, first of all, when we're talking about right triangles, let me draw in the typical right triangle that you'll see all these pictures of and show you what the labels and everything mean. So the right angle, we put that little square in the corner to represent that it's a right angle. And in a triangle, we typically call it A, B, C. So we use capital letters A, B, and C to mark the angles. Capital C is always the right angle. That's 90 degrees. And then you remember that all three of them add up to 180 degrees. And we'll get, to that a little bit more later. But then we also measure the side lengths. And the side lengths are across or opposite of each angle. So here's angle A. Side A is opposite, and we mark it with a lowercase a. Here's angle B. Side B is opposite. We mark it with a lowercase b. And then this would be side C. And that's always something called the hypotenuse, which again we'll get to in just a moment. So that is the typical labels that you will always see in right triangles. So at first we're going to stick just to right triangles, and that goes up to 90 degrees, and then we will open ourselves up in later sections to any angle, any degree, no matter how big or how small. All right, so a couple of definitions first, just so you can kind of wrap your mind around exactly what trig is, exactly what we're going to be doing, because I'll be honest, even I used to wonder what on earth trig even meant and why it mattered at all. So trigonometry, first of all, is the study of the relationships between the angles and sides of a right triangle. So when people think trig, they always think SOHCAHTOA, and that's even the first thing that pops into my mind, but it is much, much more than just SOHCAHTOA. The relationship between, sides A, B, and C, angles sides B and C, we've got lots of different equations and relationships that we have, most importantly being the trigonometric ratio. And the trigonometric ratio compares the side lengths of a right triangle. Okay, it compares the side lengths of a right triangle, meaning like how does side A compare to side C? How does side B compare to side A? And so we've got all these different ratios we can set up. That's SOHCAHTOA. We will get to that in a moment. And finally, a trigonometric function. So the ratio is literally just the fraction, numerator, denominator. And then the trigonometric function is a rule given by a trigonometric ratio. Okay, I'm going to make a list of all of those rules. Okay, so we've got the three that you know. These three are going to be familiar from geometry. Our first one is called sine. Okay, and that's how you actually spell it. Normally we just see the abbreviated version that looks like this. So we can say sine of, this is something called theta. It's basically just like a zero with a line through it. It's a Greek letter. We use it to represent an angle most of the time when we're not using capital letters. And the sine of an angle is the opposite side from that angle divided by the hypotenuse. So that's just one possible ratio of side lengths. The next one that you're familiar with is called cosine. We use cos and then that angle theta. And cosine is the adjacent side to the angle divided by the hypotenuse. That's another one of those possible trig ratios. And the third familiar one is called tangent. And we denote that with a tan, theta. And tangent is the opposite side divided by the adjacent side. So that is a third way. We are very comfortable with those three ways, I'm assuming. So remember from these, this is where SOHCAHTOA came from. Okay, and that's based off of these 9 letters that you see here. Sine is opposite over hypotenuse. That's the SOH. Same thing with cosine, CAHTOA. So that's SOHCAHTOA. You guys have probably known that for years. Just a little trick to remember which ratio goes with which name. Now we have 3 new ones. I don't think you guys have heard of these before. You may have seen them on the ACT. The first new one is called Cosecant. So this is how you actually spell it, is like that. And then we use a CSC to denote it. You may have noticed that out of these possible 3 side lengths, opposite, hypotenuse, and adjacent, these are only 3 of the possible ratios. We haven't put them in all the configurations that are possible yet. So one other configuration is that we could have hypotenuse in the numerator and opposite in the denominator. Another one that we haven't seen yet, we call it secant. We use SEC of theta, and that is the hypotenuse again in the numerator, this time divided by the adjacent side. And third, the last one we haven't covered yet, is called cotangent. We use COT for that, and that is the adjacent side in the numerator divided by the opposite side. Okay, so this way we've got literally everything covered. We've put opposite in the numerator, divided it by the other 2. We've put adjacent in the numerator, divided it by the other 2. And we've put hypotenuse in the numerator and divided it by the other 2. So we've got every possible ratio of those 3 side lengths, which is exactly what the trigonometric ratio means. So like I said, these 3 are new. We're going to be working with them right now in this first example. So find the values of all 6 of these trig functions for angle B. So if we're looking at angle B, right here, this is our focus. So the hypotenuse is always the hypotenuse. That's never ever going to change. That's the one that's across from the right angle. So the hypotenuse is 17. However, depending on what angle you're looking at, the opposite and the adjacent will switch. So the adjacent is the one that's connected to the angle but isn't the hypotenuse. So that's this side here, and the opposite is exactly what it sounds like. It's opposite from that angle. So that is this one right here. So just keep those in mind as we're coming up with the 6 trig functions. So the first one is sine. They asked us for angle B, so we're going to do sine B instead of the generic theta. Sine is opposite over hypotenuse. The opposite is 15. The hypotenuse is 7. So it's got a 15 to 7 ratio, which basically means they're pretty close in length, but the opposite is a little shorter. Next one is cosine. Cosine over angle B. The function tells me it's adjacent over hypotenuse. Adjacent is 8. Hypotenuse is 17. Now this ratio tells me that the adjacent side is actually like less than half of the hypotenuse. So you can get an idea of what the triangle is going to look like. The third familiar one from SOHCAHTOA is tangent. Tangent is opposite over adjacent. So that is 15 over 8. Okay, now we've got our new 3. So the first new one is called cosecant, and that is hypotenuse over opposite. So that's 17 over 15. The next new one is secant, hypotenuse over adjacent. So that is 17 over 8. And finally, the 6th and final trig function is cotangent, and that is adjacent over opposite, which is 8 over 15. So that is your final answer. Those are all 6 of the trig functions for one particular angle. If we switch to angle A, they would all be different because the opposite and the adjacent would change. Okay. One thing you may have noticed in this problem and up above, notice this and this are reciprocals. So are these, so are these. So notice cosecant, secant, and cotangent ratios are reciprocals of sine, cosine, and tangent ratios. So what we can say is if we're trying to find cosecant, it's just 1 over sine, which is the reciprocal. If we want secant, it's just 1 over cosine, again, the reciprocal. And if we want cotangent, it's just 1 over tangent, which is the reciprocal. So basically, we just use SOHCAHTOA to find the first 3. That's these 3 right here. And then you just remember which one goes with which, and you just have to flip to the reciprocal. So if I do these 3 using SOHCAHTOA, I remember, oh, cosecant is the reciprocal of sine, so you just flip the fraction. Same thing with secant and cosine, same thing with cotangent and tangent. So just a quick little trick there so you can get all 6. Okay, example 2. We have the tangent of one angle From there, we want to find the rest: sine, cosine, cosecant, secant, and cotangent. So the first thing we're going to do, step one that I will walk you through, is we are going to draw and label a right triangle. Okay, draw and label a right triangle. So draw it in like this. It's your standard right triangle. There it is. Okay, so now label, we've got A and B and C. So we know the tangent of B is 3/7. Now we know that tangent is opposite over adjacent. So what that means is that the opposite side to angle B is 3 and the adjacent side is 7. So the adjacent side is 7, the opposite side is 3. So that's your first step, is kind of setting up, all right, here's what I know about the triangle, and putting it into all the pieces, okay? Second step, find the missing side. Okay, and the way we find the missing side is a little something called Pythagorean Theorem, which we probably haven't used since geometry, really. Actually, we used it in the distance formula, but it relates A and B and C all together. So what we're missing is C. So we use 3 and 7. So A is 7. So we start with this. I'll write just the blank formula first. Okay, so A squared is 7 squared, plus B squared is 3 squared, equals C squared. So we've got 49 plus 9 equals C squared. Add these together, I get 58 equals C squared. And then if I square root both sides, it tells me that C is the square root of 58, which isn't something I know, but that's fine. We don't actually need to know it. And then step 3 is we are going to find the other values. Okay, so we've got 5 more to find. We need sine of B, cosine of B, cosecant of B, secant, and cotangent. Okay, so our goal is to find the other 5 based on what we now know. So now that we have this, we're going to label that right there on the hypotenuse. And so we're just basically doing the same thing now that we did in example 1. So sine is opposite over hypotenuse. The opposite is 3 over the hypotenuse, which is root 58. I don't know if you guys remember one of our rules, we can't have square roots like that in the denominator. So we multiply by root 58 over root 58. That's something called rationalizing. So in the numerator, it's just 3 times root 58. And then in the denominator, root 58 times root 58 is just 58. Okay, so kind of ugly, but that's your final answer there. Cosine is adjacent over hypotenuse, so 7 over root 58. Same thing here, we're going to rationalize that denominator, so we end up with 7 root 58 over 58. Very, very pretty. Cosecant, remember cosecant is the reciprocal of sine, so we take this original one right here and flip it. So we have root 58 over 3. Sorry, that's getting so teeny tiny. And then secant, here, let's stretch it over here. Secant is the reciprocal of cosine, so that is root 58 over 7. And then cotangent is the reciprocal of tangent. So that's actually the easiest one to find. We just flip that to 7 over 3. Okay, so that is one of those types of problems. We call those triangle problems, actually. Okay, so the next thing that we are going to look at is our special triangles, our 30, 60, 90 triangles. So go ahead and flip to these. So you guys probably remember these from geometry, so I'm just going to go through really briefly. So the way that we find the measurements for a 30, 60, 90 triangle is we start with what we call an equilateral triangle. You guys remember these? Equilateral triangles, all of the angles are the same, all of the side lengths are the same. And so then what I do is you drop down and you turn this half right here into a 30, 60, 90 triangle. So this is already 60 degrees from the equilateral triangle. And when I cut this in half, this becomes 30 degrees. All right, so now this portion right here is my 30, 60, 90. So what we do, kind of ignore this, we're trying to figure out how the sides relate to each other. So when we're doing that, we take the short side and let's just call it x. Just call that x. So this is exactly half of this. And remember, since this whole thing is equilateral, this is the same as this. So if this is x, that makes this whole thing 2x, which makes this thing 2x. Okay, so then the last thing is to find this length right here, which we use the Pythagorean Theorem for. So this is a squared. So x squared plus b squared equals 2x squared. 2x times 2x is 4x squared. And then I'm trying to get b by itself. So b squared equals 3x squared. So finally I square root. So I'm hoping these look familiar. So your last side is root 3 times x, because when I square root x squared, I get x, but I can't square root the 3. So that's this last side length right here, is it's root 3 times x. Okay, so now in order to come up with the sine, the cosine, everything like that, I'm going to do just a specific example. So let's look at one specific example of these triangles. Instead of x, let's say that this is 1, which would make this 2, which would make this root 3. All right, so we want to come up with some special sine, cosines, and tangents that we need to use. So let's do sine of 30 degrees. Okay, so if this is our 30-degree angle, the sine is opposite over hypotenuse. So the sine of 30 degrees is 1/2. That's something I'm eventually going to have you guys memorize. The cosine of 30 degrees, here's 30 degrees, adjacent over hypotenuse is root 3 over 2. Again, a special one to know. Tangent of 30 degrees is the opposite over the adjacent. So 1 over root 3, which if we rationalize that, we get root 3 over 3. You should multiply top and bottom by root 3. We also have the 60-degree angles. Okay, so sine of 60 degrees is opposite over hypotenuse, which is root 3 over 2. Oops, the cosine of 60 degrees. Here's the 60 degrees. Cosine is adjacent over hypotenuse. And finally, the tangent of 60 degrees. Here's 60 degrees. Tangent is the opposite over adjacent. So root 3 over 1, aka just root 3. Okay, so those values eventually will need to be memorized, these 6 values right here. The special triangle just kind of explains where they all come from. Okay, so here's another special triangle you probably remember from geometry, and this is the 45, 45, 90. So in the 45, 45, 90, these two angles are the same. This, of course, is a right angle. So the special thing about these two angles being the same is that these two sides are the same. So if this is x units long, then so is this. So again, like up above, we can use Pythagorean Theorem. We can say x squared plus x squared equals c squared, and then we can find that last missing piece. So combine like terms here, and then just like we did up above, square root both sides to get the c by itself. Okay, so the root 2 doesn't simplify, but the square root of x squared does, and then of course this is c. So we can label this on here. We know this one now. Okay, so this is our very generic one. Just like we did up above, I want to draw in a specific one that we can use to come up with these measurements. So here's a specific 45, 45, 90. It's easiest to just say the short side is 1 unit long because it keeps our numbers small. So if this is 1 and this is 1, this is root 2 times 1, which is root 2. Okay, so again, I'm hoping those values look familiar from geometry. Okay, so now we're going to do the sine and cosine and tangent of 45 degrees. So we can use either this one or this one, it doesn't matter. So say we use this one right here as our angle. The sine is opposite over hypotenuse, 1 over root 2, which if we rationalize, multiply by root 2 over root 2, we get root 2 over 2. Cosine of 45 degrees, cosine would be adjacent over hypotenuse, 1 over root 2, which is again equal to root 2 over 2. And finally, tangent of 45 degrees. Tangent is the opposite over the adjacent. 1 over 1 is just 1. So we've got 9 total values that will eventually just need to be memorized so we can use them. We'll talk more about them over the next couple of days. Last thing we're going to look at is these problems. We're just going to finish off this page. So using these trig functions to find x. So we've got, this is a 30, 60, 90. This is a 45, 45, 90. Okay? So one of the ways that we use these triangles to find missing sides is we look at the angle and then figure out what we have compared to that angle. So this is the hypotenuse. Compared to this angle, this is the adjacent side. Okay, so think SOHCAHTOA. Which one uses the hypotenuse and the adjacent side? That would be cosine. Okay, so we know that cosine of 60 degrees, cosine is adjacent over hypotenuse. So according to this triangle, the adjacent is x, which we're trying to find, and then the hypotenuse is 14. Okay, however, we know from up above that the cosine of 60 degrees is 1/2. Okay, so cosine of 60 is equal to this, but cosine of 60 is also equal to this. So that means we can set up a little baby equation here, like that. So if they're both equal to cosine of 60 degrees, that means that these two must be equal. So a little cross multiply x times 2, we get 2x. Multiply 14 times 1, we get 14. Divide both sides by 2, that means that x equals 7. Okay, so that should make sense based on what we know about these triangles. We know that this side is x, this side is 2x. So if this side is 7, the hypotenuse would be twice as long. So that's our first one. Last example for this video is this one down here, this 45, 45, 90. So again, we're looking at this angle right here. This is the opposite side, and this is the hypotenuse. Okay, so again, think SOHCAHTOA. Which one uses opposite and hypotenuse? And that would be sine. So we've got the sine of 45 degrees. And we have these ratios to look at. The opposite is 10 over the hypotenuse, which is x. But then we've got the very same thing going on that we did up above. We already know what the sine of 45 degrees is. Okay, so from our chart up above, we know that the sine of 45 degrees is root 2 over 2. Okay, so just like up above, we can set up a little equation. Okay, so cross multiply here. 10 times 2 is 20 equals, cross multiply here, we get root 2 times x. So to get the x by itself, I'm going to divide both sides by root 2. And at that point, so it says rounds to the nearest tenth, we could just plug this into our calculator. So I'm going to do a fraction, and I'm going to do, whoops, that's not on the screen, sorry, 20 over the square root of 2. Okay, so rounding to the nearest tenth would give me about 14.1. And since it's an approximation, I'm going to use those little squiggly equal to's. Okay, so that is the first half of your 12.1 lesson.